If only there were a way, once you have your table set up, to figure out if these differences among the groups are statistically significant. Because again, all we have is a sample. If only there were a way. There is. And what the SDA website is doing is something that I refer to colloquially as crosstabs. Cross-tabulation. Other names for this include a contingency table, the actual chart itself is something that we started at the beginning of the semester. It's a version of a frequency table. It's called a joint frequency table. When you construct these, if you think there's a causal relationship between the two variables, put the independent variable in the columns, so in our example, what was our independent variable? Depression, right? We wanted to know if you were been told that you were depressed. And our dependent variable are in the rows, and that was the suicide. Here's the quick and easy way to remember this. The letter I goes up and down. That's the easiest. That's the only way I remember this. I, up and down. So the independent variable should go up and down. Because whether you write your I like that or like that, probably should have done it like that. Okay, so that's how I remember. So when you construct these, independent variable make up your columns, dependent variables make up your rows. We can adapt the chi-square that we did last class to this. Because what we have is expectations to the outcomes. And what we're doing is comparing our expected outcomes with our observed outcomes. Now you're saying to yourself, well, wait a minute. Null hypothesis says that there's no difference. So what numbers are we going to use to create our expected outcomes? Yeah, it's a little different, right? So because we're adding another layer to our table by making it have some causality with independent and dependent variables, the math gets a little bit, well, it's not hard, you just got to pay attention. So here's the example in the book. And I have a kid, so this one amused me. And I got to go mess with my kids this weekend because I want to see if this works. Children were presented a picture of either an angry face or a happy face, and then given the opportunity to select a toy of a different color. Red, green, or gray. So what are we trying to do there? We're trying to see if the presentation of the happy or angry face leads them to select a particular toy. I got no idea how this would work or why you think this would be important. But somebody somewhere, they like to test little kids. all right, let's play this out. All right, I wouldn't experiment on my own children, but it's good to know if I can mess with them in any way. So, angry or happy face, and that'll maybe influence the color of the toy that they pick. So we create a contingency table or a crosstab. So you present them, right? I independent, the thing that you're changing. The face, and in this study they had 40 children. 20 children got the happy face, and 20 children got the angry face. When they selected a toy of 3/4, right, 75% of the children associated a happy face with the red toy. When they were given an angry face, it looks like we have an equal distribution, 7, 7, and 6. Like that's really equal. So if you were to just go off of this sample of 40 kids, it would appear in this experiment that if you give them a happy face, they pick a red toy. So the color red is associated with happiness. Why would we do that? Well, if I'm if I'm making toys, I'm going to make a ton of red toys, right? Right, you don't know, right? Because we've only got a sample of 40, which is why we need to do the analysis.
Well, red and green are opposites, too, so it could be spectrum.
See?
Like kind of blue or anything. Yeah, blue's closer to green. Like if you're looking at a color, like red is opposite on the color.
Let's just assume there's a reason. I was going with red as Santa. Like, I don't know. I'm happy. I want a red toy like Santa. I don't know. Not my field. But again, I got kids. And I'm thinking like, okay, what red toys do they have? Like, when they're happy, they pick red. Why? I don't know. If you do a useless bar chart, you can see that we really do have one that's a lot more than the other. Not that you couldn't have done that because you know that 15 is greater than 2, but... So we've got some data. We can set this up in our hypothesis testing framework. The null hypothesis, the two variables are independent, meaning that there's no relationship between the emotion you show the child and then the toy that they pick, the color of the toy that they pick afterwards. Okay. Or your alternative hypothesis is that there is a relationship between the two variables, that somehow colors are associated with emotion, and we're going to test that. Okay, so this, again, our same framework. Null hypothesis, no relationship. Alternative hypothesis, there is a relationship between the two variables. And we can follow the same process. All right. Here's something that's a little bit different with crosstabs. The degrees of freedom. Numbers of rows. So how many rows do we have? Yeah, it's written up there already. We have 3 rows because we have 3 colors. And how many columns do we have? Well, we have 2 emotions. So 3 rows and 2 columns. 3 minus 1 times 2 minus 1 is 2 times 1 equals 2. So we have 2 degrees of freedom. What isn't the degrees of freedom based off of in this test compared to other statistics? Yeah, right? So we're not looking at the sample size here at all. With the z-score or the t-test, right, we were looking at the number of observations, but with this we're looking at the number of categories or the number of boxes in our table. Another way that you might see this denoted is R minus 1 and C minus 1. R and C stand for rows and columns. All right. So we have 2 degrees of freedom. Set alpha. Alpha is always the same. Alpha is always going to be 0.05 because we're social scientists. And the critical value. Well, let's go back to our chi-square table. And let's see if I can find the extras for those of you who weren't here last class. Anybody else need one? Okay. So my degrees of freedom is 2. And I'm looking for 0.05. And that's a 5.991. So if we calculate the chi-square and it is greater than our critical value, then we can reject the null hypothesis that there's no relationship between emotion and color. In that case, what would be our excuse as to why we observed a clear difference and a preference for red when you're happy? Because 3/4 of the kids that got the happy card picked a red toy. What would be the explanation for that if, when we do our test, it comes out that there's no relationship and that we can't reject that null hypothesis? We're getting close. So the sample size might need to be bigger. Why do you think the sample size needs to be bigger? Yeah, we might have just gotten a bunch of brats that like the color red, right? I mean, those 20 kids, that red was their favorite color. Yeah. But not when they were given the angry face. When they were given the angry face, only 6 of the 20 chose red.
Those were different 20 kids, though.
They were different kids, but she said kids like bright colors. She didn't say the happy kids like bright colors. She said kids like bright colors. So we're trying to explain this difference that we observed. If we can't explain it, then maybe we just got a bad sample. Okay? All right. Here we go. You ready? So the whole row and column thing really matters. Our expected frequency is the row total divided by, or excuse me, times the column total divided by n. So expected, sorry, I felt a groan from the slide copiers. Right. Row times column divided by n. Row times column divided by n. N is going to be the same for all of these. What's our n? It's hidden down here. It's 40. Okay. Row total. So let's do row 1, column 1. which, again, I know this is annoying. This is R1 column 1. This is R1 column 2. This is R2C1. This is R3C1. R2D2. C2. R2C2. 3. Okay. So, the expected frequency of row column is the row of the row and the column of the column. This is why people often break out the N and K thing, because they're like, I think in the book they actually use I and J to make it more confusing. But just look at it and go, okay, if I'm talking about this cell here, I need the total of this row, which is 15 plus 6 is 21. 21 times the total of this column, which is 20. You multiply those together, divide by 40, and we would expect to get 10 and a half. Okay? Because 21 times 20 is 420, divided by 40 is 10 and a half. You okay, Joey?
Yeah.
Okay. Again, these are totals, right? So because we have a table set up, we can do the totals of our rows and the totals of our columns. So you see, this at least fits on the screen here. The 20s, and then you got your row totals. Okay? So you would go through and you would calculate that for each cell in the table. This is a cell. This is a cell. So if I'm doing this one here, right, I've got my row total times my column total. If I do the greens, the total of the green row divided by the total, or excuse me, multiplied by the total of the column row. Total of the column. Cells column. What do you notice about the expected values? They're the same, right? That's our null hypothesis, right? That they should be the same, right? That we should have an equal distribution from one to the other. So it shouldn't matter whether you get a happy face or an angry face. The expected frequency is reflecting that. We all cool with how you get the expected for each cell? Row total times column total divided by total total. Okay. Chi-square, we did last time. You take the difference between what you observe, which is the actual data, and the expected for each of those cells, square it to get rid of the negative sign, divide it by what we would expect and then you add them all up. Now, before you start copying, let's think about this for a second. We had 1, 2, 3, 4, 5, 6 cells. We had 2 columns and 3 rows. 2 times 3 is 6. We're going to have to do that little equation 6 times, 1 for each cell in the table. 1, 2, 2, 3, 4, 5, 6. If I were doing this, let's get back to this. If I were doing this like on a homework, I would do it like this. Hold on. Control M. Okay, this is what I would do. I would set it up as a table. So that way I could say, all right, in row 1, column 1, I observed 15. I expected 10.5. The difference between the two is 4.5, right? I would go through and do it this way. It'd be nice and neat and clean, and I can do my simple math in order. I would not try to do this. This is not how I would try to do it in my homework. Does that make sense? Okay. I think the book publisher just wanted it to fit on a slide. Okay. This is high school math. If we do them in order, right? We do our parentheses first. Was it PEMDAS? Parentheses, exponents. I don't have any multiplication. I do have division, and then addition. I don't have any subtraction in here. Okay, ta-da. So 4.5 squared minus 2.5 squared minus 2 squared, 4.5 squared, 2.5 squared, 2 squared, right? All of the signs are going to go away. So when you work through the math, what's the answer? 8.24 is our chi-squared for this example. Well, we observed an 8.24. Our critical value was 5.991. It's greater than our critical value. Therefore, we would reject the null hypothesis. Right? We all good with that? Anybody want to argue? No, we're good? Just for fun, let's take a look at our table. If we wanted a higher amount of probability. So right now we got 1 star. What about 99% confidence interval? That would be 6.635. We got that, right? So we can do 2 stars. And then the table doesn't do the one I want. It does 0.005. That's 7.8. That's really high. Right? 8.2, 7.8. Yeah, this is significant. Okay, if we were to attach a p-value to probability value of getting this outcome, it's less than 1%. Right? So we're reducing our error, right? Our chance of error. That's why they're looking at what the probability actually is. Okay. So we reject the null. Way out there. We're good. So let's draw a conclusion. Frequencies representing the color preferences of 40 infants, shown either a happy face or angry face, were analyzed using a chi-square test of independence. This analysis found a significant relationship between toy color and face, such that the distribution of the three toy colors is different for infants, shown the happy face versus the angry face. So you can scare children to choose dark colored toys, or when they're happy, they like red. Those are the conclusions you can reach.
So is it children or infants?
It's infants. An infant is a child. It's just a really little one.
But that makes it kind of random.
Apparently they do. Right? So you said, well, that makes it kind of random. No, actually, if it were random,
I know that they're all.
and the little stinkers are just grabbing a toy, then they should not be picking red for some reason. Infant psychology is not my specialty, so I can't really explain to you why infants, when they're happy, like red. I don't know. But there's clearly something going on, right? I don't think they completely made it up. Okay. So this actually is a real finding. If you get the citation from the book Meyer et al. 2009, they did this experiment. Specifically, in a happy context, red is preferred, whereas in a angry context, red is not preferred. So if you want to sell somebody something red, what should you do? Smile. Right? Make them smile. The power of statistics. Finding out how to manipulate other people. If you're in a hostile context, red is not preferred. I was going to try to come up with a hostile context and think, geez, I wonder why the red ones don't sell. But I can't come up with anything quite. I do know that if I'm like in an army uniform, I probably don't want to be wearing a red one. That's just because it's really bright and you can shoot me. Yeah, there's that too. I think I'd know. All right. Okay. So we have a chi-square. Right? We have a way to do crosstabs to see if there's a relationship. We were doing kind of crosstabs before, right? When we were doing the differences test, difference of means and difference of proportions. This is just a way to do it with nominal variables. Right? When both of our variables are nominal. One of the things that I'm, after reflecting upon the use of this book, they kind of snookered me with the title of the book, because there's not a lot of politics in this. So I said, I'm going to find the class an example of a political science article involving a very simple chi-square. And I found one. and I like this article. It's a 3-page article. You're not missing much on the 3rd page. You can get the 3rd page if you need to. And I wanted to find an article that used a chi-square to show you that even intro stats, something you're learning in your very first stat class, is useful when doing research. This guy got an article published that was 3 pages long and had a chi-square in it. You can do better than this. Right? You can write longer papers. You can, this is like, oh my God, this is so simple. Right? So what did this person do? Well, they wanted to know about the voting habits of non-respondents. So when we do a telephone survey, we know a lot about the people who answer the phone. But what about the people who don't answer the phone? So what they did was they got a sample of 608 names. Of those 608 names, they contacted those that had telephone numbers listed. And they did it, they said, will you answer a survey? Okay. They did an interview. So if you turn the page on the back, we have here completed interview, 237. So of the 428, 200, I guess they ended up only doing 401 for some reason, but 237 of them completed the interview. Then they had 37% that said, we're not going to do it. And then they had some that never answered the phone. Right? And then people who just weren't available. So they categorized the people into these nominal categories based upon whether or not they voted. So the people who completed the interview voted at 91%. The people who refused the interview, because again, remember they have their names, then they just go and look to see if they actually turned out on election day, because believe it or not, the state keeps that information on you. 89% of them voted. Well, here we have a situation where we have groups of people, different categories. So he runs a chi-square. And the chi-square is significant at the 0.001 amount. Registered voters with listed phones were significantly more likely to vote than with those with no phone listing. Okay, so the people who have telephones are more likely to vote. Non-respondent analysis was restricted to those 401 with listed telephones. They were classified as either blah, 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 blah. Post-election interviews. All right, and then it goes on. The next page just does like a vote choice analysis, but so a very simple crosstab, the basis for a published research article in political science. So I'm not just teaching you stuff that you'll have no application anywhere. You should, after this class, start using this stuff in your other classes to look smart and get better grades. Because even the simple stuff, the difference of means test, if you're writing a paper on the gender gap, comparison of groups, is valid social science research. Okay? So there, political science article with a crosstab in a published journal.